So our paper is about how can we exploit implicit feedback to improve performance of an online automated email tagging system. So I'll be briefly talking about the problem we are trying to solve and why we think implicit feedback can help us. Then I will talk about the email prediction system we have, which is part of another big project called Task Tracer. And I will also talk about the email predictor instrumentation we had to add to capture implicit feedback events. Then I'll talk about the algorithms we have designed, and in evaluation, we conducted lab-controlled user study. Finally, I'll talk about the results and conclude there. All right. So this is how an online email tagging system works. User receives an email message. The system predicts tags for the message. Notice that an email message is allowed to have multiple tags. The email user interface displays the predicted tags for the user, and this is where things get interesting. If a predicted tag is wrong, then the user may correct tags. And if the user corrects the tag, then the system gets some kind of training. However, if a predicted tag is right, then the user does not have to do anything at all. And this is the purpose of such a system. This is the goal. However, the system in this case never receives any kind of training at all. So what is the problem? The problem here is learning algorithm never receives confirmation that its predictions are correct, which is a violation of standard online learning algorithms. In machine learning, online learning algorithms assume that the ground truth tags are available after making every prediction, which is violated in this particular case. And we believe the learning algorithm would benefit from positive feedback. Before jumping into implicit feedback, we did something called survival analysis. We wanted to see how long a mispredicted tag survives before the user actually notices the mistake, or before the user actually notices the tag is wrong. So how long is measured in terms of how many interactions user have with the email system, meaning with the email message, meaning how many times the user went back and read the message, how many times the user replied to that message or saved an attachment from that message. So how many interactions user had with that message. And so it seems like in most cases, almost instantly user detects that there is a prediction mistake and corrects the tag. And the more interaction the user has with the message, the less likely that the mispredicted tag will survive. So this motivates us to explore implicit feedback, which basically is saying we can keep capturing whatever things user is doing on that email message, and after a certain point of time, if the user still hasn't corrected the tags, so we can actually kind of assume that, okay, those predicted tags are right, and then tell the training system that, okay, these are right, train on them. So in that way, we'll supply more training to the system. So that's the motivation here. Notice that important fact is implicit feedback will be noisy. It is not guaranteed to have a correct feedback, right? Okay, so this is a quick snapshot of the email prediction system we have. This is basically a Microsoft Outlook add-in we have developed. So number one here is the add-in we have developed, that the whole taskbar. Number two here shows some kind of status of the server. I'll talk a little more about the server later. Number three basically shows different predicted tags, the tags predicted for this particular message. You can click on the cross, that actually deletes the tag. Number four is a drop-down. You can create tag. These are all user-defined tags. This is your tag. So you can just click on that and add a tag on that message. Number five here shows a list of most recently used tags and a list of tags. Those are related to this message. Those are relevant to this message, but the system was not confident enough to make a prediction on the, say that, okay, this is the correct tag for this one. So these are most related tags. Of course, there is a backend server. The server is a Java backend server in our case that actually takes care of, that is actually an online multi-level classifier that takes care of all the training and the predictions. Okay, so we instrumented our email prediction system to capture whatever things user does on an email message. So that includes how many times the user read that message, how many times the user replied to that message, how many times the user changed tags on that message. So all sorts of things, we actually record everything. So we monitor whatever things user is doing on an email message. Okay, our algorithms. So we have two baseline algorithms. The first one is no implicit feedback. This is the standard behavior of our system. So this basically trains on explicit user feedback only, meaning let's say if the user adds a tag called cat on a message, then the classifier for cat gets some training. Similarly, if the user deletes the classifier, deletes the tag cat, then the classifier for cat gets training. So basically, it trains only on user explicit feedback. So this is the lower bound of our analysis here. So this sets the lower bound for all our algorithms. In contrast, the upper bound would be standard online, which basically assumes the ground truth tags are available after making every prediction. This is the upper bound for our algorithms here. Notice that this is an hypothetical upper bound because this really is not practical for this application. This would require the user to provide correct tags after every prediction, which is really not nice. Okay, so the implicit feedback algorithms we have. The first algorithm we have is a greedy approach. This basically says, we call this simple implicit feedback. This basically says, let's say this message has two tags, health and science, and the user deletes the tag health. That probably means because the user deleted health and didn't say anything about any other tag at all, that probably means it's probably safe to assume that the other tag, science, is a correct tag for this message, and remaining tag in the system are negative tags for this message. Again, notice that this is a greedy approach. This can go wrong, right? Okay, slightly better approach we think is implicit feedback based algorithm. So this implicit feedback without simple implicit feedback basically maintains a count of all those events. How many times the user did something, replied, forwarded, saved an attachment, changed flag, or moved to another folder, all those kind of things. We monitor them. And after a certain point of time, once it crosses some threshold, we say that, okay, it's safe to assume that these tags are correct for this message, and we will train on them. The third algorithm is we combine these two algorithms, basically implicit feedback with simple implicit feedback. Okay, next is evaluation. So we conducted a lab-controlled user study with 15 participants. Only email users who regularly use tags, folders, or labels, anything like that to organize their email were allowed to participate in this study. The study data, we created a set of 330 messages. We divided them into two groups, training 60 and test 270. The study was conducted in 3 different sessions on 3 different days. 1 hour, the users get to practice to learn our system and how the tag thing works, and 5 hours of performing tasks. A little bit more about the email dataset we created. So the email dataset was created keeping in mind, this was to simulate a knowledge worker's day-to-day life. In this particular case, a student who is taking 2 courses, probably maths and economics, has some hobbies like gardening maybe, and of course attends some concerts, and as a student attends meetings, events, etc. Notice that a message was allowed to have multiple tags. That's why average number of tags per email message was 1.24. And these messages basically simulated life of a student. Basically, some of the messages were completely informational about different courses. Some of the messages were group work related. So a fellow student requested to send some file or reply to some other message. Very similar to what, as a graduate student, what we do. Okay, so one of the things we noticed in the, one thing before I go to this thing. So we actually trained on those training messages and predicted tags on those 270 test messages. And the users were working on those 270 messages. Okay. So one thing we noticed is that users, oftentimes, user actually corrected tags only 16% of the time, which is actually slightly lower than what we had expected. So we actually solved it in a different way. So one thing we did was we developed this algorithm to simulate different types of user. Notice that there will be users who correct every possible mistakes. There will be some users who actually corrects tags whenever he wants, not so much, right? So this algorithm actually gives us the liberty of simulating that. We set target EF value to something. So let's say our user study had only 16% tag corrections. We want to simulate a user who corrects tags 50% of the time if there is any mistake. So of course, we have to add explicit feedback onto some messages. But which messages we want to add explicit feedback on? We decide it based on the probability distribution, probability of explicit feedback given total implicit feedback. Notice that it goes back to that survival curve. Our survival curve showed us that the more time the user spends on a message, the more likely it is that he will correct the tags if there is any mistake. So that's why we use this probability distribution to decide which messages we add explicit feedback on. Similarly, if we have to discard explicit feedback from some messages, then we use the same distribution in a reverse way. So this gives us the liberty to set different values for target EF to simulate different kinds of users. Results. So this may not be visible very nicely, but this basically shows the implicit feedback we captured for every messages. So x-axis is message number, y-axis is count of implicit feedback recorded. Those are color-coded. This is basically what kind of implicit feedback we recorded on what message. One thing is important, implicit feedback is noisy. So there will be good training based on implicit feedback, bad training based on implicit feedback, right? So we wanted to see that, okay, one of the arguments we had was like, there is a certain implicit feedback threshold where this trade-off is benefited. This trade-off is actually a good thing. So it seems like in our data set, implicit feedback threshold of 7 actually worked. So for every experiment after, from now on, actually we used implicit feedback threshold of 7. So this is the performance actually. So no implicit feedback definitely performs the worst, which is the black line. Red line is online, which is the perfect feedback that performs the best. And in between implicit feedback for 2 different target EF. Recall that target EF higher means the user is more likely to fix a mistake. Target EF lower means the user is probably not that much likely to fix a mistake. So this is for 2 different plots, we have more. And it seems like we have been able to reduce the gap between the no implicit feedback and online, which was the goal for this work. One thing is important. We argued that implicit feedback actually adds more training. So that's why this system is performing better. So we wanted to validate how much more training implicit feedback-based algorithm actually adds. So this is for different level of target EF. For, let's say, for example, target EF 0.20. So no implicit feedback adds certain amount of training. Simple implicit feedback definitely adds more training, positive and negative. And of course, implicit feedback with simple implicit feedback adds even more training. So in all cases, the benefit we are getting is probably because of this additional training. But one last question is, okay, it increases the amount of training, but are those training good? So that is this last plot. We wanted to see what percentage of the tags, what percentage of the messages confirmed by implicit feedback are actually good training examples. So this plot shows at target TEF 0.20, only 64% of the confirmed messages are actually good training examples. And it increases as target EF increases. So the conclusion from here is, although implicit feedback is noisy, on the balance, the classifier is still benefited. Our algorithm still works. Okay, so the importance of demo and deployment have been emphasized in UIST. We have a demo, please visit us. And we have a real system running, actually. 2 professors and a graduate student, which is me, uses this system every single day on our personal email messages. And this is a quote from one of the professors. It actually saves him 15 to 25 minutes per day to look up different previous messages, finding folders, and there are other uses. So in summary, automated tagging of email messages with user-defined tags is possible, and implicit feedback. By adding implicit feedback, the system actually benefits. Thank you.
Paul Ascenti at Adobe Research. So are some of these ideas applicable to other implicit feedback situations? I'm thinking in particular of implicit negative feedback. Did somebody not like something, or did they just not bother to like it? Or can some of these techniques be used to in these other situations?
I think so, definitely. I think there are online applications that has been using implicit feedback for a long time. So there are some job posting site that uses, but the difference is in this case, we have only positive implicit feedback. We cannot really say, okay, this is not a good training example. But in case of online applications like job search or movie search or all sorts of recommender systems, definitely some of these ideas can be exploited. Yes.
Thank you.
Krzysztof Gajos, Harvard. I will try to enunciate. So one thing that I really love about this work is the implicit feedback, trying to make sure that the feedback to the machine learning system really flows with what users are doing. But what surprises me about this work is the choice to automatically tag emails. It seems a very unorthodox choice for an intelligent interactive system. If you consider alternatives, if a person is already a filer, they are already used to attaching tags, then maybe you should keep them in control and make it easier for them to find the right tags. And if they're a piler, then maybe you should move the machine learning to the search time rather than the reading time. So what made you choose this particular point on the intelligence spectrum?
Okay, actually, as I said, this is a part of a bigger project. So the project is called TaskRacer. The idea is everything on your desktop should be tag-based. And you define your own tags. For example, I have like 40 tags defined on my system. Some of them are my personal tags. Some of them are project-related tags. So it's tags that have certain meaning to me. It may not have any meaning to you at all. So if everything on a desktop system is tagged, including email, files, folders, everything, then this kind of scenario can provide you additional services. For example, the next paper we will have is actually these tags will help you find a relevant folder to save an attachment. So you don't have to go through Windows Explorer and find a folder. Similarly, whenever you are trying to send a file to me, let's say, you are not trying to send some file, random files. Probably you are trying to send some project we worked on. So this kind of tags things will actually help you find those files very quickly. So this is coming from a bigger project. This is one small part of it, actually. I don't know if it answers your question. We can talk more in the demo, maybe.